Well, welcome to the last section of Chapter 9. This section is on tessellations, and this is kind of a fun section. We're going to work on identifying figures that will tessellate or will not tessellate, and we're also going to identify the transformations and symmetries that exist in tessellation. So what is a tessellation? Well, oftentimes you'll hear a tessellation referred to as a tiling of a plane. And basically what that means is you have a pattern that repeats over and over, and there are no gaps or overlaps in that pattern. We make tessellations by using translations or rotations or reflections. And we see these kinds of things everywhere around us. You can see it in art, you can see it in nature, and just in your own home you might have some kind of linoleum or pattern in your floor or carpeting where it's a tessellation pattern. So some of these shapes, they fit together in repeating patterns that fill a plane without gaps or overlaps, and that the angle measures of the polygons that fit together like that have special relationships, and we're going to talk about those. So here's our first example from art, and it says, what is the repeating figure in the tessellation, and what transformation does the tessellation use? Well, the first step, we're going to try to answer the first question, what is the repeating figure? And if you look in this figure, I don't know how well this is going to copy onto your printed notes, but there's a tan colored fish here, and then there's a blue colored bird, and there are two red turtles as well. So the first step is to identify the repeating pattern. And in this example, it's the tan fish, the blue bird, and two red turtles. Okay, so once you've identified the repeating pattern, the second question is what transformation does it use? And if you just look at this pattern, it looks like it's a rotation. Here in the very center, this would be the center of rotation. And so that one is definitely a rotation. And that angle of rotation, since that occurs 3 times, would be 360 divided by 3, which is 120. So we've identified the angle of rotation. The tessellation uses a 120-degree rotation about the center point, which is right where the noses of the fish meet. Here's a couple examples. What is the repeating figure in the tessellation, and what transformation does the tessellation use? Well, in letter A over here, this one, it looks like a lizard, I guess. And you'll see a red one, and then a black one, and a white one, and then a red one. And it repeats over and over again. So see if you can try to find how many of those are in a pattern. If you look right here, here's the center of rotation. So it goes red, black, white, red, black, white. So there's actually 6 of those. And so that would probably be a 60-degree angle of rotation. So it's the one lizard, and it definitely is a rotation that's happening. They didn't ask us to find the angle of rotation, but had they asked that, that would be 60 degrees. It would be 360 divided by 6, which gives us 60 degrees. How about this one over here? Well, I see a white bird going to the right, and then a blue bird that flies to the left, and that just repeats over and over and over again. And that one looks like it's a translation. You'll see the white bird, and you can just move it to the right, or you can move it down by translating it. And the same thing with the blue bird. So it's the white and the blue birds, and that's definitely a translation. So how do we figure out whether or not a figure will tessellate? Our question in this problem says, does a regular 18-gon tessellate? Well, the thing we need to find out is what would a single angle in an 18-gon, in the interior angle, what would that angle measure? And back a few chapters ago we had the polygon angle sum theorem, which gave us this formula. The measure of an interior angle of a regular 18-gon is 180 times n minus 2 over n, where n is the number of sides in the polygon. So we're going to substitute in for the letter n right here, the number 18. And when we do that, we get an interior angle of 160 degrees. So that's our first step. Then what we need to do is figure out, is 160, is there a multiple of 160 that will give us 360? And if we multiply it by 2, we get 320. If we multiply it by 3, we get 480. And there is no integer multiple of 160 that will give us a complete circle of 360. So it's either going to overlap or be a gap. So therefore, an 18-gon will not tessellate. How about a regular hexagon? See if you can think through that one. Would a regular hexagon tessellate? What would you have to figure out first? Well, what's the measure of an interior angle of a hexagon? Using that formula, we have 6 sides in a hexagon, and when we plug that in the formula, we get 120 degrees. So 120 degrees, is that an integer multiple? Is there an integer multiple of 120 that'll give us 360? Well, yes, we can multiply by 3 and get 360. So does a regular hexagon tessellate? The answer is yes, it does, because it's an integer multiple of 360, so there would be no gaps. So one of the other things you should know is that it doesn't have to be a regular polygon in order to tessellate. All triangles and all quadrilaterals tessellate, and here's a couple of examples here. If you notice the point of rotation in here, we'll always add to 360, and you'll notice that there are each one of these angles occurs twice in a 360 degree rotation. So you have the number 1 red angle here and here, and then number 3 occurs twice, and number 2 occurs twice. And then over in this one, each one only appears once, but there's no gaps there. Just make sure that you know that there's no gaps and it's a complete circle. Every tessellation has at least one type of symmetry. Over here on the right-hand side, we have regular hexagons, and there's reflectional symmetry in these hexagons. Each one of these blue lines represents one of the lines of reflection. There's also rotational symmetry. I could rotate this thing 60 degrees and I would have rotational symmetry as well. And there's also translational symmetry. I could just translate any one of these hexagons up or down one, and that would be right on top of another one and you wouldn't notice the difference. So there is translational symmetry. And also glide reflectional symmetry. Okay, glide reflectional is when you can translate something and then reflect it over a line. So let's just say you took, I'll draw this one in here, maybe this will help visualize this one. Take any one of these hexagons and translate it to the right, and then you could reflect it about a line right here, and then this one would be the image. So that would be a glide reflection. We've talked about those in our last section. So those are the different kinds of symmetry in that figure on the right-hand side. So what kinds of symmetry does this figure have on the right-hand side with these triangles? Well, if you look at this, there's definitely some rotational symmetry going on. Okay, each one of the centers of the triangles indicated in red in the video here, you could rotate 120 degrees, and that would have rotational symmetry. You could also translate any one of these triangles. If you take any one of the vertices and translate it along a straight line to the next vertice, that has translational symmetry as well. So that one has both rotational and translational. How about this one down here? This is an interesting kind of a figure. And it says, what types of symmetry does the tessellation have? And if you look at this one, I'll help you out a little bit by putting in maybe these lines of symmetry here. See if you can see what I'm doing here. There's a couple of lines of symmetry in that figure. If you reflect along those lines, you'll get an exact replica. And how about this one? I also noticed these 2 lines of reflection. So there's definitely reflectional symmetry. That should help you visualize those. There's also rotational symmetry. Okay, I could rotate this thing about an axis and still have the same pattern, and it looks like it's probably a 90-degree rotational symmetry. There's translational. I could take any one of these kind of hexagon shapes and translate it either up or down or left or right. And there's also glide reflectional as well. Here is your lesson check. What is the repeating figure in the tessellation? Just describe what the repeating figure is. And what transformation does the tessellation use? And then just like we had in the video, can you tell whether a regular 15-gon will tessellate? And what types of symmetry does this tessellation have? Bring those answers to class. We'll see you next time.